Welcome to Engineering 626. This is the first lecture for Engineering 626, and in this course we're going to be talking about the development, or trying to learn about the use of numerical techniques to solve problems in electromagnetics. This field is referred to as computational electromagnetics. And we're going to start with one of the most straightforward techniques in computational electromagnetics, and that's the finite difference method. Now, I'm not talking about the finite difference time domain method. We might talk about that later in the course, but for right now, we just are going to have finite difference method for static cases where there's no time variation. We start with one of Maxwell's equations. The divergence of D is equal to rho. Here del dot is the divergence operator, and D is the electric flux density, and rho is the free charge density or electric charge density. And now the way that D, the electric flux density, the way that that's related to the electric field intensity, E, which is probably more familiar to you, is given by this equation. We see that D is equal to epsilon times E, where epsilon is the permittivity of the medium in which these fields exist. And here we just have a note that the units for rho, as we've already said, rho is the charge density, and the units for rho are coulombs per cubic meter. So this is the amount of charge per volume. Now, as I already mentioned, we're interested in the static case. We're not going to allow any time variation here at the beginning. Maybe later in the course we will get to some time varying problems, but not right now. So in this case, in the electrostatic case where there's no variation in time, we can define an electric potential V that is equal to is related to the electric field intensity E by this equation. E is equal to the minus gradient of V. So let's see if we do this and substitute into this equation, into this one of Maxwell's equations, what we obtain. Well, first we're going to use this equation, which tells us that D is equal to epsilon E. We're going to substitute that in here, so we get the divergence of epsilon E is equal to rho. That's directly from this equation, simply by substituting epsilon E for D. And now we say, okay, we're going to suppose that epsilon is constant, which just means that the medium under consideration is a homogeneous medium. It's not changing. And so if that's the case, then since epsilon is constant, okay, so here we go. So here's the question. Here's the equation we have now. When we substitute epsilon E for D, we get this equation. And as I said, if epsilon is constant, then of course it can be brought out of this divergence operator, and so we have epsilon multiplied by the divergence of E is equal to rho. So as we were saying here, I'm sorry I've gotten a little distracted there. But since epsilon is constant, it can come out of the divergence operator, as we've seen right here. And furthermore, since we're talking about the electrostatic case, then we can substitute minus the gradient of V for E. And so that's what we've done here. Now the minus sign of course can come outside of the divergence operator as well, And so we're left with minus epsilon. And now this is for the case where we have a homogeneous medium, so that epsilon is constant, and where it's also the electrostatic case, so that there's no variation in time. But we end up with minus epsilon times the divergence of the gradient of V is equal to rho. And so if we bring the minus epsilon over to the other side of the equation, then we get this equation that says the divergence of the gradient of V is equal to minus rho over epsilon, and the divergence of the gradient of V is the same thing as del squared. The Laplacian, this operator del squared is called the Laplacian operator, and this is so the Laplacian operator operating on V, the electrostatic potential, is equal to minus rho over epsilon. And this is an important equation in electromagnetics. It is called Poisson's equation. And once again, remember that the assumptions built into this equation are that we have the electrostatic case, which means that there's no variation with respect to time, and also that the medium under consideration is homogeneous, which means we don't have different kinds of materials present in that region, that there's all of one homogeneous material. It could be, it doesn't have to be vacuum, it could be some material medium, but the important thing is that it's not changing in the region under consideration. So again, this is Poisson's equation, and if we furthermore assume now that we're in a charge-free region, then rho is equal to 0, and so in that case the right-hand side of this equation will go to 0, and we end up with del squared V is equal to 0. And this is another important equation in engineering, and it's called Laplace's equation. And this is the equation that we're going to be dealing with here in the beginning part of this course. Let me read this for you. It says, for the beginning days of this course, we're going to consider the use of the finite difference technique to solve Laplace's equation over various regions with various boundary conditions. So that's our goal in our first few classes, is to learn. We're going to take this equation as a good example, and we're going to learn how to use the finite difference technique to solve that equation over different regions with different boundary conditions. Okay, so now just a brief reminder in case you are a little bit rusty with this. The Laplacian operator acting on V, this del squared acting on V, gives you partial squared V, partial x squared. This is if you're in Cartesian coordinates. It gives you partial squared V, partial x squared, plus partial squared V, partial y squared, plus partial squared V, partial z squared. And again, if we're considering Laplace's equation, then del squared V is equal to 0. So we have the sum of these second derivatives of V, second partial derivatives of V is equal to 0. Notice that this is a second order partial differential equation. Second order because we have second order derivatives. It's a partial differential equation because these derivatives here are not ordinary derivatives. They are partial derivatives with respect to x, y, and z. Or another way of saying that is that V is a function of the three independent variables x, y, and z. It's not a function of t, but it is a function of x, y, and z. So V, the electrostatic potential, is varying in space, and for the moment we're considering the possibility that it can vary in all three directions, in the x direction, in the y direction, and also in the z direction. So that's how we get the full-fledged equation right here. Now, some of the kinds of problems that we will consider, we're not going to solve or unless some of you have a particular interest in it, we probably won't try to solve any three-dimensional problems where the potential can vary in all three directions. We will probably be satisfied with just looking at problems in two-dimensional regions. And so here's an example of two kinds of problems that we might consider. In this first one, we have a rectangular region where V might be specified on the four boundaries of the rectangle, and then we want to find out what V is equal to in the interior region. Or another possibility, and this is another two-dimensional problem, we might have a circular region where V is specified on the outer boundary of some circle, and we want to know what V is equal to in the interior of the circle. One of the advantages of both of these problems is that we can solve for V analytically. And what I mean by that is that we can solve it by hand, and that's nice. Now, of course, you might say, well, if we can solve the problem by hand, then why would we want to go to the trouble of writing a program to use some computational technique? And you're right. In general, we don't want to write programs to solve problems that we can already solve analytically. But we can also say that in general, we can't solve problems analytically. In general, the problems that we're interested in will be so complicated that they just can't be solved analytically. And so that the spirit of what we're doing here is that since we're just learning the numerical techniques here, we're not trying to solve any very complicated problems yet. Eventually that will be the goal, but right now in this course we're interested in just learning the techniques, and so it's convenient to apply those techniques to problems that can be solved by hand, because then once you get your solution, you can compare it to the hand calculated solution, and you can see how accurate your numerical solution is. And that will give us a lot of insight into, well, first of all, it will help you to debug your program. If your results are far off, that gives you a hint that probably there's something wrong with your program. But in other cases where you're pretty confident that your program is working correctly, it will help you to see when the technique is more accurate and when it's less accurate, because none of the techniques that we will study in this course will be perfectly accurate. There'll be error in all of them, and so by comparing our numerical solutions to analytical solutions, we'll be able to get a better handle on that idea of which technique is more accurate and under what circumstances it's more accurate. Now, an example here of a more complicated problem is right here. If we see, as this note says, regardless of the boundary conditions, this problem with this boundary here cannot be solved analytically. So you can see we don't have to make much of a change. It doesn't have to be some very exotic region for us to get into a situation where it can no longer be handled analytically. Here, the rectangle can be solved analytically, the circle can be solved analytically, but when we put half of a circle with a rectangle, now we can no longer solve this by hand. And so, you see that it's very easy to find a situation where it's just too complicated to be done by hand. And so, if we learn how to use the numerical methods for simple regions like this, it'll be fairly simple to apply them in a slightly more complicated situation like this, where the analytical solution is not available. So just this statement here is basically just summarizing. So for now, we're going to go ahead with Laplace's equation plus boundary conditions. And remember that Laplace's equation has built into it that there's no variation in time, and that the region under consideration is homogeneous, and also that it is charge-free. So those are the assumptions, and here's our equation, and of course this is a second order partial differential equation, so we're also going to need boundary conditions to solve it. Now, so this is where we are, and let's take this as sort of our starting point. Now, this next sentence says, for today, let's make these even simpler and assume that partial y equals partial z equals 0. So, and again, this is just to get across to you, to make things simple and get across to you the very basics of the finite difference method. So we're going to take away, we're going to assume that v, and this is only for the moment, we'll go to the more complicated case soon, but for the moment we're going to assume that v does not vary in either the y or the z direction. It can only vary in the x direction. So that's since v is only varying in one direction, this is referred to as a 1D world, or one-dimensional world, that varies only in the x direction. And our equation, when we take out the variation with respect to y and z, then Laplace's equation just becomes this. And notice that not only have we dropped out the two partial derivative terms that involve partial derivatives with respect to y and partial derivatives with respect to z. Now, clearly those have been dropped out, but notice one other slightly more subtle change is that this second partial derivative with respect to x has now become an ordinary derivative, and the reason for that is that if v does not vary, remember we've already assumed some time ago that v is not varying with respect to time, and now in this particular example we're also assuming that v does not vary with respect to y and z, and so that means it's only varying with respect to one variable, and that is x, and therefore this partial derivative becomes an ordinary derivative. So here is our ordinary differential equation, and we'll have boundary conditions at the ends of this region. We'll say that the region is stretching from x equals 0 to x equals L, and so we'll have boundary conditions at those two boundaries. And the idea then is that you suppose that we know v at the right boundary, we know v at the left boundary, and we want to find v in between those two boundaries. And we want to do this numerically using the finite difference method. And again, in the interior region, since there's no time variation, and the medium in there is constant, and there's no variation with respect to y or z, and there's no charge, since all of those are satisfied, we can say that in this region d squared v dx squared is equal to 0. Now, we can have different kinds of boundary conditions. One would be, one example of the kinds of boundary conditions we could have is v of 0 is equal to a and v of L is equal to b. When you have a boundary condition that involves knowing the value of v on the boundary, that's called a Dirichlet boundary condition. On the other hand, another example would be if we knew the partial derivative of v with respect to x at 0 or at L. So we might, for instance, have partial v partial x at 0 is equal to a, or partial v partial x at L is equal to b. Those are called Neumann boundary conditions, where when we have a partial derivative, boundary condition on the partial derivative, that's called a Neumann boundary condition. We can also have mixed boundary conditions, where it is a boundary condition that involves both the function itself and its derivative. So all of these kinds of situations can arise in practice. But for our first problem, we're going to take the simplest case, which is the case of the Dirichlet boundary conditions. We will assume that v is equal to a when x is equal to 0, and v is equal to b when x is equal to L. Now, as we begin to think a little more about how we're going to solve this equation, one of the first things we realize is that we want to solve it. We want to find v in this region between x equals 0 and x equals L. And of course, there are an infinite number of points between x equals 0 and x equals L. But the first step of and of course, we can't solve an infinite number of equations on a computer. So the first step of the finite difference method is to identify specific points in this region where we will try to solve for the unknown. And these points are called nodes. And so you can notice here that we've put one node at the left endpoint, one node at the right endpoint, and then we have other nodes in between. And for right now, we will assume that those interior nodes, we can refer to these as interior nodes, and the two nodes on the boundary are sometimes called boundary nodes. We can assume right now that the interior nodes are evenly spaced. Now that's a restriction that we will be able to relax later on in the course, and we'll look at what happens when we have non-uniform spacing of the nodes. But for right now, let's assume that the spacing is constant, which means the distance between this node and this node is the same as the distance between this node and this node, or between this node and this node, or this node. The spacing between any two consecutive nodes is the same. Okay, and now let's see. So we're going to enforce the differential equation, d squared v dx squared equals 0. We're going to enforce that equation at the interior nodes, and at the boundaries we will enforce the boundary conditions. Remember, at v at 0 is equal to a, and v at L is equal to b. So those are the equations that we will enforce at those nodes. So now